So today we're going to continue looking at how you figure out what molecules look like. And we have looked at spectroscopy, we've looked at IR, and now we're going to go ahead and turn to spectrometry, which is where you measure a spectrum, but not necessarily an electromagnetic spectrum. In this case, we're going to measure a mass spectrum, and so that we call mass spectrometry. So mass spectrometry is a technique for measuring molecular weight and determining molecular formula, and you can also determine some structural information as well. So when you want to acquire a spectrum, you put a small amount of sample, like a microgram or milligram, into the inlet of the mass spectrometer, and it's vaporized. And the sample then enters the ionization chamber, where it is ionized by an electron beam. And so this is a really high energy beam, like 1600 kilojoules per mole, compared to, on the order of 100 kilojoules per mole of bond strength. So this electron beam hits the molecule that's put into it, and it ejects an electron, and that results in a positively charged ion. And so then the ions are accelerated into a magnetic field, and the analyzer selects for ions of a given mass to charge ratio. And these detected ions are amplified and recorded to give the mass spectrum. So looking closer at what happens in that ionization chamber, the molecule is put into the mass spectrum, injected into the mass spectrum. This is the high energy beam, and it will kick out an electron. And so when you remove an electron from a molecule, you're left with something that's positively charged, and there's going to be an unpaired electron as well. So we call this the molecular ion or the parent ion. And this has the same molecular weight as our original molecule does. So this radical cation can then start to degrade into various different radicals and cations. And because their radicals are neutral, they don't get, their path is not impacted by the magnetic field. Only the cation's path is impacted and changed. And so these are the fragments that we end up seeing in a mass spectrum. So if you see it in the mass spectrum, it's got to be charged. So the mass spectrum, here's a simple one of methane. And what it has is it has on the vertical axis this relative abundance, and the highest peak is always going to have this 100% mark, and we call that the base peak. And in this case, the base peak is the same peak as the methyl radical cation at 16 m over z. So down here at the bottom, we have our mass to charge ratio, that m over z, and z is the charge of the ion and m is the mass. And typically z has a +1 charge, and so really this is just the mass of the ion that's being observed. Okay, so as I was saying, the methane has a molecular weight of 16, and you can see down here that the mass to charge ratio of of this peak to the right is 16, and so we call that the molecular ion or the parent's peak. There's also a little tiny relative abundance here to the right, and you can see that it's called the m+1 peak. So it's tiny, and we'll come back to what that comes from in a minute. So since Z is always 1, the charge is almost always plus 1. M over Z measures the mass of the individual ions. So as I mentioned, the tallest peak is called the base peak. In this case, the base peak is the same as the molecular ion peak, but it won't always be that way. All right, so let's look now at the M+1 peak and recall that carbon ions have, well, most of them have an atomic mass of 12. And so for most methanes, the carbon in it is carbon 12. And so that's going to be the most common type of methane, the one with carbon 12 in it, and that has a molecular weight of 16. But a couple of carbons, some carbons, a small percent, 1.1%, has a mass of 13 instead of 12. And so if you look to the right here, you have this very small peak, 1.2 percent, is a methane that has a C13 in it instead of a C12. Okay, so in the mass spectrometer, you get your molecular ion peak and then that fragments, as I've mentioned. And what happens for methane is you start to lose hydrogens. Okay, and so that's what you see as these smaller peaks. Those are fragments of methane. Okay, and so this would be the CH3, CH2, CH, C. Notice these are all carbocations, so we can see them in the mass spectrometer. So you can see sort of a similar pattern in a more complicated molecule, or the mass spectrum of a more complicated molecule. Here, the base peak is right here in the middle. Let me circle that. I can find my, I can't. Maybe I'll circle it. Maybe I'll put a little square on it. Whoops. Let's try that again. How about an arrow? There we go. Base peak right there. And that's actually different in this case from the molecular ion peak. And so when you're looking for the base peak, that's pretty easy to tell. It's going to be the tallest peak. It's sort of defined as having the mass relative intensity of 100%. The molecular ion peak is a little bit harder to distinguish. Basically, what you want to do is go to the farthest right peak on your mass spectrum, and then note that there's probably going to be a little M+1 or maybe an M+2 peak. And so then look for the bigger peak just to the left of that. So this is the one that I have the arrow to over on the right is the most likely molecular ion peak. But you can see that there's still these clumps of peaks. And so what's happening is we have our molecular ion peak, and that's of course the molecule minus an electron. And then, here it's, let's see, we go from 72 to 57, so that's minus 15. So it's lost 15 AMU. That's probably losing a methyl radical. And then we lose minus 29. That's probably loss of an ethyl radical. This thing is 29, so that probably is an ethyl radical, and it's lost the rest of its molecule. So you can tell a little bit about the molecule, the structure of it. We know it has a methyl group. It probably has an ethyl group in there as well. So these are the sorts of things that you want to be able to do when you look at a mass spectrum. You want to be able to determine the base peak, which we just did, and determine the parent peak or the molecular ion peak. And that's this one down here. This is the same spectrum that we just looked at. Now, from the parent peak, you can figure out some proposals for the molecular formula. And so the way that you would do this is, if we look down here, we see this is 72. And so we'd say, okay, that's 72 AMU. I'm going to divide it by 12 to figure out the maximum number of carbons. So that would be 6 carbons. So maybe I just have 6, maybe my molecular formula is 6C or C6. But that's not very likely for an organic molecule. Plus we can see that we've lost methyl groups and ethyl, so there's got to be some hydrogens in there. So this isn't just C6. So let's take one of those carbons and we're going to convert the 12 AMU to hydrogens. And so instead, so C6 is one option. But we could say, well, actually maybe it's C5 and then H12. And so this also has a molecular weight of 72. We could even say, well, maybe one of those carbons and 4 of those hydrogens are actually an oxygen instead. So maybe it's C4H8O. And that also has a molecular weight of 72. And so you can just go on like that until you kind of run out of reasonable things that could have molecular weights or reasonable molecules that could have molecular weights of 72. Now, if you wanted to draw a structure of this, it's nice to have a little bit more of an idea of if there are double bonds or I don't know, something else in there. So we can use a formula called the degree of unsaturation or the hydrogen deficiency index. And we actually already have done this before. If you look at C5H12, that has the relationship between carbons and hydrogens as being CnH2n plus 2. And so that would be an alkane. So maybe it's pentane, or maybe it's 2-methylbutane, or 2,2-dimethylpropane. Could be any of those. This one, on the other hand, is C4H8O. And so you might not know what the oxygen does to that kind of idea. Are there double bonds in there or not double bonds? And so what you can use, like I said, is this degree of unsaturation. And what it says is you multiply the number of carbons that you have and you add 2. And then you don't have to do anything with the oxygen, you just ignore them. And then you divide by 2. Got to put your hydrogens in there, or subtract your hydrogens, pardon me. So if we look back here, for this one, we have C4H8O. So plugging into this equation here, we have 2 times, whoops, dog's here, 2 times 4, because we've got 4 carbons, plus 2 minus hydrogens. We just kind of ignore the oxygens, and then we divide this whole thing, divided by 2. And let's see, our number of hydrogens, what did we say? That was 8, right? Okay, so we divide that whole thing by 2. And so we have 10 minus 8 divided by 2. So that equals 1. So that means we have 1 degree of unsaturation. So we have a C4H8O with 1 degree of unsaturation. So that might be like a ketone, for butanone, which would be a 4-carbon chain with a ketone in it, or maybe the aldehyde or something like that. So I think that's probably a good place to wind up here. Here's a couple of examples of more complicated molecules and figuring out their degrees of unsaturation. You can see once you get those benzene rings in there, that's 4 all by itself degrees of unsaturation. And so all of these drugs have pretty high degrees of unsaturation. They've got lots of rings and double bonds.